So this session is on deploying Tight-SLA services on an IP backbone. So the objective of this session is to present design and deployment good practices to enable Tight-SLAs to be offered on an IP backbone. So the idea is to be pragmatic and to overview the technologies that you should use, and to see which one is useful and how to use it and in which condition, and to back up this analysis with validation results. So the idea is to give operational guidelines, and this is based on deployment experience. So the focus is on the backbone design. So what we will see here is focus to deployment. So 50% of what I'm explaining is already deployed, and the other 50% is being deployed at this time. So it's pragmatic. The overview of the analysis is as follows. When you look at tightening the SLAs of an IP backbone, I think that 50% of your attention is going to be driven on controlling, optimizing loss, latency, and jitter. The 50% of your focus will be on optimizing the convergence. So how fast the network is going to reroute upon a link or node failure to minimize the length of time that the loss of connectivity lasts. In order to control or optimize the loss, latency, and jitter, the technologies that you would typically look at are diff-serv, TE, and diff-serv TE. So in this context of this session, which is a summary of a one-day tutorial that I presented at Ripe and Apricot, we will quickly only overview the diff-serv part. So I'll try to summarize what you would learn with the TE and diff-serv TE sections, but the focus is on diff-serv. And for the other 50% of our attention to tighten SLAs, in the convergence plane, we're going to look at technologies such the IGP sub-second convergence, and then other technologies that allow you to go one order faster in terms of convergence, which should be MPLS fast reroute. And once again here, my focus in this shorter presentation will be on the ISIS sub-second convergence. And the reasoning with this choice is that what you will see is that there are technologies that I think are really must consider, which is diff-serv and ISIS sub-second convergence, while the MPLS-based technologies have a non-negligible deployment cost. And so it's important for these ones to understand on a case-by-case basis what is the network that you look at and whether you meet the conditions that ensure that the benefits those technologies will give you are higher than the cost that they will cause. So if you want to have further information on this content, we publish a paper in Computer Network, Engineering a Multi-Service IP Backbone to Support Tight-SLAs. And I gave also this tutorial at Ripe 41 in January and at Apricot in April. So you can get the full day tutorial at this URL. And basically this tutorial is only the visible part of what I do inside Cisco, which is to focus on helping the deployment of these designs by producing low-level designs, so text documents that explain how to configure the routers, and especially to back them up with validation results to make sure that the design idea works, but also that the technology works. So the agenda of this session, this presentation, is in 4 steps. We have an introduction on SLA just to position what we're going to optimize, and then we will overview the sub-second IGP convergence and the backbone diff-serv design, and then we will conclude. So once again, it's a very short summary of the one-day tutorial. So, for example, the SLA introduction is going to be very short, and I'm going to skip quite a lot of concepts. So typically, when a service provider looks at a class of service design for the backbone, he will consider 2 or 3 classes, 2 or 3 aggregate classes in the backbone. You'll have one that is called the real-time or the voice-over IP class, where you will have commitments in terms of throughput, availability, loss rate, delay, and jitter. Typically, you will have a second class of service that is called the premium data or the business class, which will certainly have commitments in terms of throughput, availability, and loss rate. Quite often, it will have a commitment in terms of delay. And then you will have the third aggregate class of service, the best effort or the standard or the internet class, which will have commitment in terms of throughput or availability. Sometimes you might find commitments in terms of loss rate or delay, but they will be much looser than the commitments that are given for the business or the voice over IP classes. And so, while this presentation is being focused on the backbone, the focus of the work that is behind this is on looking at the end-to-end SLAs. And when you tackle this problem, you soon see that you soon realize that you need to decouple the problem in two steps. You analyze the problem in the backbone and you analyze the problem at the edge. And so either you're going to sell edge SLAs or backbone SLAs or end-to-end SLAs, but technically you're going to divide the problem into sub-problems. So this session is on the backbone problem, and if you're interested, there is the same kind of material for the edge as well. At the edge, you would typically see in a deployment much more classes of service than this. Why? Because the congestion is going to be higher. So you need to segment the bandwidth between more classes. So I expect that I can skip the definition of the throughput, availability, loss rate, and delay. They are kind of intuitive. And I'm going to only overview three SLA metrics. The first one is the one-way jitter, which is generally computed as the variation of the delay for two consecutive packets. So the factors that influence the jitter are a variation of the propagation delay. So either is the SONET infrastructure or the routing change the path. If you change the fiber distance by 1,000 kilometers, it means that you have a jitter of 5 milliseconds. So this cause is actually quite important in realistic context. Another factor that causes jitter is variation in the time it takes to switch or process a packet inside the router, excluding any scheduling delay in input or output queues. And then you have the variation of the time you spend into the queues, either on input or output, which is the scheduling delay. So the jitter, you have the variation of the delay when you sit in a queue waiting to be sent onto the wire. For those applications that do not like jitter, they will use digital buffers that basically will transform a variation of delay into a fixed latency. And so typically you will see that it will introduce fixed latency into your system. So when we look at this design guide that has been deployed in the summer of 2001, so what you see here has been deployed, what we were looking at in that case was a budget for the voice over IP service of 100 milliseconds of fixed latency between the mouth and the ear of the speakers. So 100 milliseconds, we needed to subtract 30 milliseconds just for the propagation delay on the backbone, 6,000 kilometers diameter of a US backbone. We needed to also take 35 milliseconds on average in terms of voice over IP processing, such as coding, decoding, packetization, depacketization. So which means that our design had to make sure that the jitter that would be caused in the network would not be higher than 35 milliseconds. And because the target was an end-to-end SLA, we had to deal with the edge problem and the core and the backbone problem. The problem at the edge is much more complex than in the backbone. So out of the 35 millisecond budget, we allocate 30 milliseconds to deal with the jitter at the edge, which means that the edge designs will optimize for a worst-case jitter on each access direction of 15 milliseconds, which means that for our design for the backbone, we have a target of 5 milliseconds of jitter for the backbone. So it's a back-of-the-envelope computation, but if you assume on average 10 ops, it means that in order to achieve this target, I need to make sure that I don't have more than 500 microseconds of jitter per hop, per IP hop. So that will be the target, one of the targets for this design, and you will see at the end validation results that show that this target is actually quite easily achievable with nowadays technology. Another SLA metric that is often forgotten, while still when people design IP network, that's often a rule that they follow. The fact that when you do load balancing, you do it on a per flow basis. And the reason that this performance metric is important is that because if you have reordering of packets within a flow, it is going to impact the service perception of the customer in three different ways. For long-lived TCP traffic, you will see that the throughput is going to be degrade. If you have a video application, you will see that the reordering rate will equate to a loss rate. So it will increase the loss rate perceived by this application. And then the effect of reordering on voice over IP is actually quite different in that the reordering is likely to not affect voice over IP in itself, because the inter-packet gap between voice over IP packets is 10-20 milliseconds. So it's not likely that reordering will be such big that you will actually have packets that are out of order. However, the cause of reordering is likely a cause of jitter, and so that's the cause in this case that we need to eliminate in the design. So this is a result from a paper from Michael Lauer that analyzed the effect of reordering on long-lived TCP traffic. And you see that as soon as you introduce like 0.04% of reordering on a per flow basis, the achievable throughput for the TCP traffic is reduced by 20%. And if you inject like 4 or 5% of reordering, then the throughput is reduced by 40%. Another performance metric that is often forgotten in the context of Tight-SLA is the impact of convergence. So indeed, when a link fails or a node fails, the network is going to take some time to reroute on the new best path. And in the meantime, you will have a loss of connectivity. This loss of connectivity is going to affect the service that is perceived by the customer. For voice over IP, it's obvious. Typically, the service providers, the requirement that they express is that this loss of connectivity should be less than 1 or 2 seconds to make sure that the voice over IP gateway or the human being that use this application will not drop the code. So that's the first target we have in terms of loss of connectivity. Some of the service providers will have requirements that the loss of connectivity should be smaller than 50 milliseconds. So it's a target that we work on, but I must say that technically I've never seen any reasoning to say that indeed this 50 milliseconds was really something that you had to achieve. So if you know why, I'm interested. Another impact of this performance metric, the convergence speed on the SLAs or the service perception, will be on availability. So it's quite tight, but if you would look at a 99.999% availability per day between 2 points, you see that it equates to 900 milliseconds of downtime. A typical convergence in an IP backbone will be 10 seconds. So you blow this target in just one link failure. So you see the impact of this performance metric, so you want to optimize it if you care about tightening your SLAs. So that's a quick overview of the SLA context in which this work takes its place. So in the remaining of this session, we're going to look at the technologies that we're going to use to optimize those SLA metrics. So in order to optimize the loss, latency, and jitter, we're going to look at the overprovisioning system for the backbone. We're going to look at differentiated services, at the impact of capacity planning, and normally if we would be in the one-day tutorial, we would look at TE and disk of TE. So here, we will not cover the TE and disk of TE part. And then the other focus of the presentation is what are the technologies that you could use, when should you use it, how should you use it to enable an optimization of the loss of connectivity and optimization of the convergence. We will focus here on ISIS sub-second convergence. The other technologies that you should consider is MPLS fast route, and depending on the time I might try to quickly summarize what would be the info you would get with the one-day tutorial. So let's start with the sub-second IGP convergence. So IGP backbone convergence, I define it as the time it takes for connectivity to be restored upon a link or node failure for an IP flow that starts on an edge access router and that ends on another edge access router, excluding any variation of BGP routes. So you have BGP routes, but you don't analyze the flapping of those routes because it's something exterior to your backbone. You care about the convergence of the backbone. And in the context of this session, the IGP that is analyzed is ISIS. The validation data that I'm going to give is for ISIS. So we might do the same kind of validation work on OSPF. Normally it should behave in the same way, but I did not do it in the context of this project. So we might do it if we would have a requirement from what we call a lead customer that will agree to deploy this. So historically, the ISIS convergence that you would get is on the order of like tenths of seconds. It's quite poor, and it's explained by the fact that historically people have not really cared about optimizing SLAs or convergence. What this presentation will explain you is that if you take a default iOS image with default timers, and in the context of the lab measurements that we have, that I will explain later, which is in summary 1,000 ISIS nodes, 4,000 ISIS prefixes, and 140,000 BGP routes. When we fail a link, if you take default ISIS configuration, you will get a convergence on the order of like 8 seconds. And if you follow the suggested low-level design that I'm going to explain, you will see in our lab we validate the convergence below the second. So that's what you're going to see with this first part of the session. So first step is to quickly overview what a link state protocol is, how ISIS work, in order to highlight the steps that we need to optimize. So if you are interested in more details, that's basically where we spend much more time in the one-day tutorial to explain in detail those basic steps so that you understand what we need to optimize. So we take this example network, and we're going to sit on this node here. This is the root where we are, and we're going to look at how this node is going to compute the routing table. So the first step to compute the routing table is to build what is called the shortest path tree. The shortest path tree is the set of all the shortest paths from this node to all the other nodes. The typical algorithm that is used to compute the shortest path tree is Dijkstra. So you see that as soon as you think about optimizing convergence, you will think about optimizing this computation because it's the basis of the building of the routing table. And so here you see that if I take this topology, this is the tree that I'm going to compute thanks to Dijkstra. And if suddenly I lose this link, basically you need to recompute Dijkstra to rebuild the new updated shortest path tree rooted at this node. And you see that the two trees are different. So as soon as you have a change, you need to compute the shortest path tree in order to compute the routing table. So this will be one thing that we're going to look at in terms of optimization. The second step is that, well, you have the shortest path tree, which is the set of all the shortest path from you to the other nodes, but this is not what you care. What you care is the routing table that is expressed in terms of prefixes. So the second step is to use the shortest path tree to actually build the routing table, which is called the RIB, the routing information base. And so logically, that's not the way it's done in the code, but logically you can picture it like this. Once you have the tree, we graft leaves on this tree, and the leaves represent the IP prefixes that are locally connected to those nodes. And so logically you can view that once we have the tree, we're going to walk this tree, and every time we find a leaf, we're going to insert it into the routing table because it's the shortest path to get to this prefix. And so, once again, if we care for fast convergence, we want to optimize this process of building the routing table. The third process that we're going to also look at is that the routing information base, the routing table, it's not the information that is actually used directly by the router to switch the packets. The table that is used to switch the packet is a reduced, optimized version of the routing table, which is called the forwarding information base. And so the FIB is what is actually used by the data plane to switch packets. The FIB is an optimized image of the routing information base. So if you take a router, you would typically see that at the highest level of the control plane, you will have the best route per protocol, so show IPBGP, show ISIS database. They will try to inject the best path into the routing information base, and then once the routing information base is built, it will be transformed into a forwarding information base that is downloaded to the line cards to ensure forwarding. And once again, this step needs to be optimized if you care about fast convergence. So now that we have described the context, we're going to walk through a set of optimization to explain why we can achieve a faster convergence with today's technology. The first step is to optimize the SPF computation. So the first thing that a human being would do is that if there is a change in the network that doesn't impact the tree, you should not recompute the tree. You take the tree that you computed before and you just update the routing table with the change in terms of leaf. This is the first optimization. It's called PRC, partial route computation. So you have this network, the same as the one I showed before, and you see that in dashed, it's the links that have not been used for the shortest path tree routed at A. And in red, you see the links that form the shortest path tree. If suddenly A learns about an LSP that tells him that there is a new leaf connected to F, with PRC, A will be smart enough to not recompute the tree. And so it's a big gain because the tree computation is eliminated. So you take the tree that you computed it before, you just add the leaf, and then you just see that you need to add this leaf in the routing table. So typically a PRC will almost cost nothing because it's just the incremental addition or deletion of the route that has changed. The second optimization you can bring to this process is incremental SPF. So again, the idea is that a human being would do the following. If he knows, he just learns that the topology is affected, that indeed the tree might have been modified. A human being is likely going, when he looks at a map and some roads have changed, he's not to recompute the whole set of shortest path from him to any of the nodes. He's going to kind of visualize what is the part of the graph that is affected. And so he's going only to fix up the part of the tree that is impacted. And this is the second optimization, incremental SPF. So it's much smarter because, for example, if you are in this case where suddenly A learns that this link disappeared, well, A with incremental SPF is smart enough to say, well, I don't care because that link was not used for my shortest path tree. So even if the graph is modified, my tree is still the same. So my routing table is still the same. And so you do nothing in this case. Another case where you see a maximum gain is that suddenly you add a new router to the network. In that case, again, most of the tree can be kept, and the only operation you need to do is to graft a new node on the tree. So incremental SPF will say, all the tree is not affected, all the routes that are connected to this tree do not change. The only thing I need to do is to graft this new node, compute the new outgoing interface and next stop for this new node, and then add the leaves, the IP prefixes that are locally advertised by this new node. And so in this case, you will have again a maximum gain because it will go very fast. So how does it work? It's an optimization. It's an algorithmic optimization to the Dijkstra algorithm, where you put more information in the tree in order to be able to fix it up instead of rebuilding it from scratch. So most of the all the ISIS optimization that I'm going to describe has been coded by Stefano Previdi, is here at the back. So if you want to ask any question, he's around and he'll be happy to talk about this. Now the question is, how much gain do you have from incremental SPF? It's difficult because non-deterministic. It depends where the modification of the graph occurs. So if this is the tree, and I'm here, If, for example, I add a node, you see that this change is very far away from the root, so it affects a very small part of the tree. So here you have maximum gain, because incremental SPF will really do the minimum required compared to SPF, which would rebuild everything. If, however, the change occurs here, so much closer to the root, then you see that the gain is smaller. In this case, it would be more or less visually a 50% gain. So it depends how far away the change is from you. So in this internal project where we do validation, that's more or less one of the steps where we are. So we're trying to devise a good formal framework to qualify the gain you have. So based on ISP topologies and iterative what-if scenarios to kind of compute what would be the average gain we see. We have some early results from EFTs, but it's difficult to, I'm not going to quote them because it's not coming from a very formal test bed, but it looks like interesting. So if I summarize the first optimization, if you detect that you only have a change of IP prefix, of leaf information, your graph is not affected, then the tree can stay like it is. And you only need to tweak the routing table with this leaf that has been affected. This is PRC. In terms of impact on the graph, topological impact of the graph, there you have the normal scheme, the historical way to deal with this, which is SPF, which would recompute the whole tree and then recompute the whole routing table. Obviously, even this historical or old scheme did not scratch the routing table and rebuild it. You always do it incrementally. So you keep your routing table up to the point where you know that this route you need to remove it and replace it by another one. You don't delete it and then recompute it. It would be silly. And the optimization to this scheme is to do incremental SPF. So when you see that your topology is affected, you keep the part of the tree that is not affected and you only fix the part that has been modified, and you only recompute the part of the routing table that depends on this part of the tree. The second set of things we're going to look at to optimize convergence are the topology and leaf optimization. So here it's more design rules that you can apply to help the convergence of your network. The first one is actually you don't need to think about it. ISIS is doing it for yourself in iOS. So when you have parallel adjacencies between two nodes, ISIS will only advertise a single adjacency. So it's an optimization that we put in the code. I could find out when, but it's quite a long time ago. And so it's good because your graph is going to have less links, so the computation will be faster, and your topology is more stable because if one of the links disappears, well, it will not cause any new LSP flooding because you still have another link adjacency that is parallel and that is still there. So that's the first optimization. The second optimization is to treat the point-to-point GE interface that you often have in the POP when you have two routers interconnected by back-to-back GE. ISIS, by default, treats such a case as a multi-access network. And so in the database, it's going to represent this as two nodes interconnected by a third node called a pseudonode. And this is very unoptimal because it introduces one extra node and one extra link. So the advice, the suggestion is to, when you have such back-to-back GGs, is to configure those back-to-back FEs, GGs, or 10 GGs in ISIS network point-to-point, which will tell ISIS this is not a multi-access network. There are only two routers. So just model this into your database just like a post link. And so in the database, it will be modeled as two nodes interconnected by a link. The difference is that you save one node and one link. So when I presented this at RIPE in January, the European SP that is that is about to deploying this came during the break and told me, well, by doing this we save 300 nodes. So So they had 300 back-to-back DDs in the network. It's a set of 300 nodes. So it's a very easy thing to do, which can have a big impact. The third thing that you might think of is to minimize the number of leads you have in your IGP. The only minimum thing you need to do is to carry the BGP next up. All the other interfaces, you don't need to have them in ISIS. The only thing you really need are the BGP next up. And so that would be the optimum. If you want to implement this, you can use rather ISIS, advertise passive only. It will only advertise the loopbacks into the ISIS topology. And so you would use IBGP to carry all the addresses of the interfaces that you have inside your network. The gain you have is that it is going to speed up the routing table construction. And so it will be useful for BGP because BGP relies, you have this isolation between exterior routes and interior routes. And so BGP recurs on the next stop. And if you have a very fast convergence of your next stop, BGP benefits from it because it falls back on it. And if you make your ISIS topology too big, it will converge less fast, and so you impact BGP in the same time. So really, in this case, you don't need to carry the interface's address in ISIS. So it's one thing to consider when you want to optimize for fast convergence. The next set of things we're going to look at to optimize for fast convergence is the tuning of the timers that control the most important operation of ISIS, which is to run SPF, to run PRC, so to run this algorithm that allows to update the routing table, and the timers that control how fast the router is going to rebuild an LSP when an adjacency has changed locally or a prefix has changed locally. So the purpose here is twofold. You want to have these timers such that if the network is stable, you converge very fast. You react very fast to the events. However, if the network becomes unstable, you want to avoid a collapse, and so you want to slow down the reaction to the events. So the purpose of the timers I'm going to explain here is to achieve this best of both worlds. Very fast behavior in stable times, and slow behavior if the network becomes unstable. The type of timer that we use to achieve this behavior is called backoff exponential timers. So it's a timer that is going to be dynamic, that is going to adapt itself on the basis of the stability of the network. This adaptation is based on three values. The initial wait, or if you want the smallest reaction time, which is going to be used when the network is thought to be stable. A maximum value, which is going to be the worst duration, the longest duration that you will apply when you think that the network is unstable. And then between this very fast behavior and this very slow behavior, the third parameter is the exponential seed that will determine how fast you back off your execution to go to the very slow behavior. So let's take an example to show how it works. So these timers are in iOS since quite a long time. They've been rarely used because they are quite non-intuitive, and that's due to backward compatibility reasons. So I'll try to explain it. It's much easier than what it looks like. The first value is the maximum value, and it's the first value for backward compatibility reasons. It is expressed in seconds. So that's the maximum value that you will take between SPF execution. The one in the middle and the last one are expressed in milliseconds. These were the optimization of these timers. So the middle one is the initial wait. the smallest duration you will wait. It's here 100 milliseconds in this example. And the last one is the exponential seed, which determines how fast you go from the slow behavior, the fast behavior to the slow behavior. And here it's 1 second. So let's take an example where, for example, at this time you receive an event which is an LSP that tells you that an adjacency has disappeared. So it tells you you need to execute SPF to rebuild your routing table, or actually to update your routing table. So if you receive this event, this new LSP at this time, let's assume that at that time you are in stable behavior. So the router is going to say, I'm in stable behavior, something has changed, I'm going to not delay SPF very long. I'm going to go in very fast behavior. So I'm going to schedule my SPF execution in 100 milliseconds, which is the initial wait. And so 100 milliseconds after, you execute SPF and you update your routing table. Let's say that some new LSPs are received right after this SPF execution. The router is not going to say, well, I just executed an SPF and I still receive events to ask me to execute SPF. So it looks the network is becoming unstable. So I start to do the exponential backoff. And so at this time it's going to say, I'm going to schedule the next SPF in 1 time the seed after the occurrence of the last SPF. So this is the seed, and so the next SPF will be executed 1 second after the last occurrence of SPF. Obviously, if in the meantime you received over events, so over LSPs, you will process all these LSPs at the next SPF here. So if after the second SPF you still receive an LSP with a change in the topology, the router is going to see, indeed, the network looks like less stable, and so I keep on doing the backoff behavior. This time I'm going to schedule the next SPF in 2 times the seed, and then it will be 4 times the seed, and then 8 times the seed. So in this case it will be in 2 seconds. And again, if you have other events that occur in the meantime, other LSPs that arrive, you will process them all at the next occurrence of the SPF. So, and if the scheme goes on, you will go to 4 times the seed, then 8 times the seed, and so on, up to a maximum value, which is, in this case, 10 seconds. Now, you see how it behaves. If you are in a stable behavior, this is the parameter that will always be used. That's the one that matters. If your network is stable, you receive an LSP that tells you something has changed, the router will wait this middle parameter before executing SPF and updating the routing table. If the network becomes unstable, it quits the fast behavior and it slows down its execution in order to save CPU and to avoid a collapse. And so it will be, in the worst case, 10 seconds in this example between SPF execution. Now the question is, how do you go back from an unstable behavior into a stable behavior? And this implementation does it like this. If the router sees a period of time of 2 times the maximum value, so here 20 seconds, without the reset of any LSP, it declares the network as being stable again, and so it sets the timer to the initial wait again. And so the next LSP that would be received would be processed 100 milliseconds after in this example. So you see that with this scheme, you can target very fast reaction, fast convergence, without any trade-off of stability. The problem with those timers was maybe the explanation of them, but also the default values. When they have been introduced in iOS, well, the guy that did it did not take much risk, and the default values are quite slow. So basically that's why that by default, even if you have those timers, you'll have a quite slow convergence that do not really benefit of the intelligence of the timer. So for example, the initial wait, so the smallest duration you will wait between receiving an indication that something has changed in the network and actually the execution of SPF to update your routing table will be 5.5 seconds. And this is not needed. If your network is stable, you can process it right away. So before giving you some suggestion on how to tune those timers, here is the reason behind this suggestion. We want to optimize for the bad news. We want to optimize for the loss of an adjacency. And in Dijkstra, in this algorithm that is used to compute the shortest path tree, this the routing table, you will only consider an adjacency between two nodes if it is reported by both ends. So it means that we don't need to wait for the two LSPs coming from the two nodes that have lost this link. As soon as we receive one of the two LSP that says that the adjacency has been lost, we know that SPF will execute this link. And so we can really tune the thing to react fast to the first behavior. We don't need to wait for a second one. So the suggestion that I give here is to tune the initial wait to its minimum value, which is 1 millisecond. You receive something, you execute SPF right away. And it's okay because if your network is unstable, you will back off exponentially to a slow behavior. So you can take the risk to be very fast. Because if your network is stable, and that's what I see in the networks that we look for this deployment, the occurrence of the LSPs, the average time between LSPs is quite large. So you can, in stable condition, do this SPF right away. What would be the suggestion for this exponential seed? The suggestion is to take the average time it takes for your router to compute SPF. So in the network that we were looking at here, it was 50 milliseconds that SPF duration typically was on this network, so we back off by 50 milliseconds. What is the maximum wait? The idea is that you want in unstable behavior to have a CPU utilization of, for example, 1 divided by 10%. So you want that your CPU spend less than 10% into ISIS if the network is unstable. So it means that you want your maximum wait to be 10 times, more or less, the average SPF duration. And so that would be a suggestion to set the maximum wait time. And so these timers are available, are going to control the SPF execution, the PRC execution, and also the building of the local LSP when, for example, you lose a link with a neighbor. If you lose a link with the neighbor, you need to rebuild your LSP, so this piece of the jigsaw that you're going to communicate to your neighbors so that they can reconstruct the map and compute the routing table. You have, again, a timer like this that is going to control how fast you build this LSP and then how fast you flood it to your neighbors. And you can follow the same kind of suggestion for this timer. The next set of things we need to look at for the optimization of convergence is the pacing and the flooding. So what is it about? ISIS works in a distributed manner. If there is a change in the topology, you need all the routers to converge to the new routing table. Otherwise, you will not have an end-to-end consistent path between your access routers. So this flooding operation is the operation that ensures that you communicate the LSP, this jigsaw puzzle that describes a local topology, to your neighbors so that they can compute the new routing table. There are two behaviors that we look at here. The first one is called pacing. Pacing is the behavior where when you talk to your neighbor, you're going to pace, to rate limit, the speed at which you send new LSPs to him. Because historically, if you send LSPs too fast to him, he might get congested, its input queue might get congested, or the CPU is busy doing something else, and eventually this adjacent router would drop some LSPs. And this is very bad for convergence because then you fall into loss detection and recovery. And this is really not optimized for speed. So you really want to avoid missing an LSP. So that's why you need to pace, to make sure that you don't burst too many LSPs at your next up, at your adjacent router. Here, the default value in iOS is 33 milliseconds. Historically, we know it works well. At a high-level view, I think it's too long for nowadays technology, but I don't have any validation results that I could use to back up a reduction of this time. So my suggestion is keep the default, 33 milliseconds. It's anyway quite small, and we have experienced that it's a good value to make sure that you don't have loss of LSPs with your neighbors. So this one, keep the default. The other behavior that we need to look at is the trade-off between being selfish and not being selfish. So what do I mean here? If my neighbor sent me an LSP that indicates that there is a change in the topology, the question is, should I be selfish and compute my local routing table and then flood this LSP to the neighbors? Or should I not be selfish and so flood the LSP to my neighbors so that they can themselves compute the new routing table, and then I will compute my routing table? If you look at this trade-off, you will see that you have case studies, so scenarios, where both schemes are better. However, overall, we think that it's better to flood first and compute SPF after. And here I cannot give you too many details because it's close to the implementation and there is no need to explain what is proprietary, but at least high level, there was a lot of optimization when we did the validation for this. Here, to achieve this good trade-off between flooding first before doing SPF, while still having the safeguard that if we are in an unstable situation and we keep receiving LSPs, at a certain time we stop being too nice with the neighbors and we take the time to execute SPF and then continue with the flooding. So there was quite a lot of optimization done in the code. We reach the last section on the optimization to increase the convergence of your backbone, and it is to review the impact of your link protocol onto the convergence at the layer 3. There are two properties that you need to care about. The first one is the link failure detection. So the faster and the more reliable the failure detection is, the better it is. The other property that you want to look at is the dampening for flapping links. That is, if the link goes down, you want to very fast detect it and communicate it to your layer 3. However, if the network goes back up, you want to make sure that the link goes back up and is stable in up position. If it goes up, down, up, down, up, down, you don't want to bother the layer 3 with it. So you want to dampen this flapping links in down position if you have a flapping links. And so this is the second property that is important when you look at a fast convergence design. So the first interface type that we're going to analyze, and the most important one, is POS. So you'll see POS is the best link protocol available if you care for fast convergence. So if you are in design time for new network, use POS if you care for fast convergence. So first analysis, how fast the link failure can be detected. Well, POS is excellent because it relies on SONET and SDH link management protocol. So in a couple of milliseconds, depending on the fiber distance between the router and the failure, you will detect the link failure. So you know that the SONET SDH is going to very fast, in a few milliseconds, detect the failure. So here in our low-level design for an IP network, we care about how fast the implementation is going to communicate this detection at the SONET SDH level to the ISIS level. In iOS, but I would guess that another implementation would have the same kind of timer, you will find 3 timers to control this. The post-delay trigger line timer is the hold time before reacting at layer 3, it's the hold time before reacting to a new line alarm. The default value for this delay is an immediate action, so it's 0. The post-delay trigger path is the hold time before reacting to a new path alarm at SONET level. And the default action in iOS is to not react to it. The third timer is called carrier delay. It's the hold time between the end of the post-delay hold time and the bring down of the interface, and so the communication of this failure to ISIS. By default, it is 2 seconds. So let's analyze how you should, a suggestion for the tuning of those timers. Carrier delay, it's something that is available for different types of interfaces, so it's generic in iOS, but for POS, it's not useful. So the default value is too slow. So if you care for convergence, one suggestion is to configure it to 8 milliseconds. That's the result of the validation we did. So 8 milliseconds for the carrier delay. Basically it means that as soon as you detect the POS alarm, you bring the interface down and you tell it to ISIS. Now, what about the delays what about the delays at the SONET or SDH driver level between the notice of a new alarm and actually the bringing of the interface to a down position? So there are 2 timers there. So it depends what kind of infrastructure you have at layer 1, layer 2. If you have a protected SONET network, then the suggestion is to allow for this protection to occur. So you would configure like a delay of 50, 60 milliseconds for the post-delay trigger line and path to allow the SONET network to protect for the failure. If you use an unprotected SONET network, then as soon as you detect the alarm at either path or line level, you want to react as fast as possible at ISIS level because you don't have anything to hope from the SONET network. And so you should configure those timers to 0. So the line is in gray when the default value is actually the one you want to configure. So it means you don't need to do anything for this one. If you have DWDM between the routers and you have a protected DWDM, then the alarms you will see are only at line level, so you don't care about the path alarms. And again, because you want to allow for the DWDM network to run its protection scheme, you will delay the reaction by 50, 60 milliseconds. And finally, if you run it over an unprotected DWDM network, again you want to react as fast as possible, and basically you see that here the default timers are good for you. And the only thing you need to do is to reduce the carrier delay, because here you have the other 2 timers and it's really redundant. So the carrier delay is not set to 0. Maybe if you do your own validation you will see that it's good for your case, but when we did the validation for that part of the low-level design, if we set it to 0, we have some noise in terms of debug, so we have some noise on the router because it reacts too fast to some alarms, and so setting it to 8 make a very stable behavior where we see no noise. Now so we saw that with POS we have a very fast link failure detection. We saw a suggestion on how to tune the timers. Now let's analyze the bring up, so when we clear an alarm. And again, POS is interesting here because by default, POS, and I think it's written in the standard for SONET SDH, will wait for 10 seconds before actually clearing the alarm. So the clearing of the alarm needs to be confirmed for 10 seconds before you actually clear the alarm. And so it means that with this behavior, you protect yourself with a POS interface for flapping behaviors that have a period less than 10 seconds. If the period of the flapping is longer than 10 seconds, then this scheme will not help. But still, it's a good behavior you have with POS. So POS is the best link layer that you can use if you care for convergence. It will give you a very fast link failure detection. Really, do not tune I-SPF hellos if you have post interface. It will give you no benefit. It will only cause you problems because you make your network less stable for nothing. So don't tune them down. And post is also nice for the way up because it will confirm that the link is indeed back up for 10 seconds before communicating it to I-SPF. What about other interface types? The first one that comes to mind is Ethernet. The good news is that FE, GIGI, and 10 GIGI in back-to-back mode. So the IEEE is working on an extension of the link protocol for this kind of configuration, where the preamble, some bits in the preamble are reused to actually have a link management protocol for Ethernet. And basically the same kind of technology as it is used for SONET SDH is being retrofitted into Ethernet in back-to-back configuration, in full duplex configuration. So for our hardware, we're close to have it on the GIGI interface. So as soon as you have this kind of technology, it means that the same kind of fast convergence you have with POS, you'll have it also with GIGI-based network. In the meantime, if you have older hardware, or if you have ATM interface, or other type of interfaces, then indeed you will not have the same kind of link failure detection, and so you will need to rely on a tuning of the I-SPF hello and hold time. So this is the fastest behavior that you can configure currently with iOS. So it means that the hold time is 1 second. So the worst case duration it will take to detect a link failure, the loss of an adjacency, will be 1 second. We did, because again the lead customer for this low-level design is mainly POS. We did not do yet the validation for this fast LO configuration. Again, if you don't need to do it, if you have POS interface, don't do it, because you see that here, if for example you have congestion on output, and suddenly your hellos span 100 milliseconds on output, and again 100 milliseconds on input on the other neighbor, it's 200 milliseconds. Let's say it's 4 times bigger, and then you could lose an adjacency due to the congestion on your link, while actually the adjacency is still there. So there is a trade-off here that you need to analyze in detail, and so here I don't have any validation result for this configuration, but I've seen it being deployed. Should I cut here? So we're changing the tape for the video. Is there any question students for a long time until you make sure, until the up status is confirmed? Frankly, I don't know what is the status with this one. I think it's in EFT, but in the context of the validation, we did not yet reach that level. So that would be the full solution to that problem. Now, if you look at the full day tutorial, and if you want to still go forward with this design, and you don't want to necessarily delay until you have an iOS with this feature, you'll see that there is a suggestion to the way the LSP generation timer, on how to program the LSP generation timer to actually try to work around that problem. I could not explain it here. It will take me 15 minutes and then I'll be out of time. But read that slide. I think it's in the pack here, or take the one-day tutorial, and it's a workaround to try to have a kind of interface dampening thanks to the timer. But the full answer is this. Can I go? Can I restart? Yeah, okay. So let's go on. Okay. So the next topic in the one-day tutorial is to overview a few guidelines on how to operate this design. So it was a good idea from the lead customer behind this project, which said, when you do the validation, please ask your testing engineers to keep track of all the good ideas they have to operate it. And then when we go through deployment, we also remember what we learned in terms of good operating practice. So unfortunately, I skipped the whole section because I don't have the time, but you have the slide, not in this pack, but the one on the web. So let's try to summarize what we learn in terms of suggestions for low-level design for fast convergence. POS is the best link type you have currently, thanks to the link failure detection that you have from SONET and SDH. You do not want to tune ISIS hellos if you have POS. It will give you no benefit. You want to tune the different timers that a typical implementation will have to control how fast we communicate the alarms from SONET to ISIS. So the carrier delay, you should tune it down if you care for fast conversions. The post-delay trigger line and path, you want also to tune them on the basis of the SONET SDH infrastructure or DWDM infrastructure you have. In terms of design work, when you build your network, you want to minimize the number of ISIS nodes. For example, you use the point-to-point mode for back-to-back GTs in a POP. You want to minimize the number of links. You use an iOS with the adjacency reduction when you have parallel adjacencies. You put your back-to-back GTs in point-to-point mode. And then you want to minimize the number of prefixes. So I know that some networks run with lots of prefixes in ISIS. There must be good reasons for other targets, but if your objective is fast convergence, you don't want to do it. You want your ISIS engine to be very fast, so that BGP that relies on the BGP next hop is going to be updated very fast. So there you can use ISIS advertised passive only to only keep track of the loopbacks, the BGP next hop into ISIS. And then all the interface addresses, you advertise them via internal BGP. Another optimization that you might want to look at is the optimization to the algorithm that I use to build a routing table. So when you only have a prefix change in your network, you don't want to rebuild the SPT. You just want to tweak the routing table for the prefix that has changed. This is called PRC. If you have the tree that has modified, so the topology that is impacted, a node that disappears or a link that disappears, you don't want to recompute the whole tree. You should use an optimized SPF that is going to keep the tree that is not affected and only fix the part that has been modified by this failure. And finally, you need to tune the timers that control how frequently, how fast SPF, PRC, and LSP generation operations are going to be executed when the router detects that it needs to do it. And there, it was a suggestion, that's the one we use in the validation, on how you could tune those timers. The idea is, thanks to those adaptive dynamic timers, to have very fast behavior in stable network, in a stable network, and if the network becomes less stable, to back off to a slow behavior. So, the validation results that back up the low-level design. The first results that I'm going to explain are quite old. We did them maybe in November, with, no, I'm sorry, it's back in September. So it was 12019S. Carrier delay was configured to 8 milliseconds, so all the time. So here it's already a 2-second gain. And what we analyzed in this first test result is the difference between tuning and not tuning the SPF, PRC, and LSP-Gen timers. This is the lab we have for this validation. We have a replica of the inner core. We have two POPs, the top POP and the bottom POP. We have agilents, we use an ISIS simulator to inject 1200 nodes and 4000 prefixes into the ISIS topology, so to make it big. We use Agilent router tester connected to the access router in the bottom POP, another one connected in the top POP and then in the bottom POP, so behind this access router. We send 10,000 packets per second from A to B, 10,000 packets per second from B to A. This is the shortest path in normal situation, and we fail this link. So we fail this link, and the packet path will be this one after the failure. So what we measure is the number of packets we lose from the time we break the link until the packets are rerouted on the new best path. And so the number of packets we lose multiplied by 0.1 milliseconds give us the convergence time. And it's good to do it like this because it's a black box testing. It's not good to look at how much time you spend in SPF. It doesn't mean anything. It's only one part of the convergence. But you need to also update the routing table. You need to propagate this to the line pass. You need to flood and so on. So there are many more things that you need to look at. So doing this black box testing is more meaningful. So we have BGP between all the access routers, and we have 144,000 BGP prefixes in the test bed when we do the testing. When we did this test, this was the average duration for the SPF, so the building of the tree, 100 milliseconds, and this is the result. So we always do 10 times all the test. You see that the results are consistent, so it's quite consistent. You see the big bars are the convergence time measured for default iOS, so no tuning of the timers. In this case, the convergence is in 5.6 seconds. If you tune the timers as suggested, the convergence measured was 650 milliseconds.
Was any stuff in the link properly that they had there, the propagation delay to load the LSP to the floating that wasn't in your lab?
Could you?
It's in the lab, right?
Yes, we did it in the lab.
So you didn't have link propagation delay to the factor?
Yeah, you don't have the latency, so you don't have the propagation latency, which is a fixed value that you can add to those numbers. So, for example, if you care about a link failure in SFO that needs to be propagated to a router in DC, if you think that the router in DC is going to be the one that is important to really choose the new best path, which is not likely, it's likely to be closer to this, but still, it's only 6,000 kilometers, so it's 30 milliseconds. So propagation latency, you can add 30 milliseconds. So now the question is, and that's very important, is yes, 30 milliseconds is the time you spend on the fibers to communicate this information, but how much time do you lose at each hop for the flooding? And that's why I said, well, it's very important to optimize the code for that behavior. And so that's one of the things that we optimized. When we started the testing, the behavior was not always the best one we wanted to have. So the optimization of the flooding is important because if you take 100 milliseconds at each hop to do SPF, and then you flood. If you have 10 hops, then you wait 1 second.
How long did it take for all the BGP traffic?
So it's the next test. Good question.
You mentioned about starting time to be in the second measure. And you mentioned optimization. Do you know about what we can expect now?
For the flooding?
Yeah.
At each hop?
Rather than after flooding, but get to measure the it's better now with about 50%.
I don't have a value, but what is important is that I cannot tell you if it's 2 or 8 or 6 or 7 milliseconds, but what is important is that it is not 100 milliseconds or 500 milliseconds. It is not after SPF. That's what is important. How much time? It's a few milliseconds, maybe less, but I don't have a number to give you. I have a value, for example, for RSVP. It's a bit the same, but so it would be like 5 or 6 milliseconds. So I would guess that it's like a couple of milliseconds, but I don't have data to say this. Okay. So this testing was with carrier delay configured to 8 milliseconds. So now this testing is to show that if you don't, so this is what we measured before, so the average of the test iterations. And if you configure carrier delay to its default value in the same test but you redo the link failure, you would measure 2.6 seconds of convergence. So it means that really tuning the carrier delay, which is simple, it's only one line, will give you 2 seconds of speed up. Usually we did not do it. It's one of the things that I learned when I went through this low-level design guide. Well, I did not know before that carrier delay existed in iOS, so guess you did not know either. So the next test is actually one step further, and when we look at fast convergence, it is not for the pleasure of looking at fast convergence. Well, the technology is interesting, but we look at it for service. The service that is behind this objective is most likely voice over IP. If it's voice over IP, it's between gateways that are on-net, that are managed by the service provider, in the cases that I know. It means that the destination, the applications, the host that receive this information and that care for the fast convergence are within your network. And so when we look at it with the lead customer for this, initially they thought to advertise it into a BGP. And actually one of the results of this is that it's a good idea to advertise this in ISIS actually, to have the fastest convergence. It's the obvious thing, because BGP has a bit more complexity in terms of convergence, because it recurs onto the ISIS next hop, and so you'll need to update it. Still, you can have a very fast behavior if your network has load balanced path between access routers, which is shown in this test. So you have 2 access routers, and there are 2 or more, but in this case 2 equal cost paths from this node to this node. So the 2 equal cost paths are, you see the yellow path and the green path. And so we're going to also measure convergence for traffic that is sent at 10,000 packets per second to BGP routes. And we'll have 3 BGP routes. BGP1 and BGP3 are on the green path. So they've been load balanced on a per flow basis on the green path. BGP2 has been load balanced on the yellow path. We're going to fail a link along the green path. And we're going to measure the convergence for the ISIS next hop, but also for the BGP, the 3 BGP prefixes. And this is the results we get with this testing. In this case, it's a reduced topology. It was 500 ISIS nodes, 1,000 ISIS prefixes, 80,000 BGP prefixes. There was no reason to change topologies because this has been done at different times in the past month. The accuracy is still 0.1 milliseconds, and what you see is the result of 10 iterations of the test. So in blue you have the average, and in red you have the standard deviation. You see that in this test bed, the ISIS, the convergence, the loss of connectivity for the ISIS next hop, so the loopback of the access router in the other POP was 300 milliseconds. Now, for BGP2, the loss of connectivity is 0 because BGP2 has been recursed onto the IGP path that is not affected by the link failure. And so you see that what you were expecting, no loss of connectivity, is actually what we see in the test. Now the big question is, what is going to happen to the BGP routes that were recursed onto the ISIS path that is going to be affected by the failure? And you see that it's on the same order of magnitude as the convergence of the next hop, which is a very good achievement, and actually, to me, beyond expectation, knowing it.
How many of those 8,000 BGP prefixes, I guess, recurs to that ending?
They all, 40,000 recurs. You divide it by 2, it's always symmetric. So 40,000 behind me and 40,000 behind the other one. But again, it's a good behavior. It's a very good behavior. I was surprised when we managed to go to this behavior. So this is like an optimization. It's not in SCS code right now. So if you would like to test it, it would be EFT code right now. But in terms of design, it's not that needed, because the application that care for the fast convergence typically will be voiced between gateways that are on net, and so the recommendation that is in the design guide would be to place those routes into ISIS. But that's a plus. So the conclusion... I'm sorry? Then it's not like this. Yeah, but it's a technical workshop. So if you ask the question, it's, I guess, because you know that the technology behind this is quite complex. So once again, and we're going to do the TOS. There can be lots of nasty questions, but the world is never all good. But the art of designing is to put yourself in the good behavior. And I think that for the realistic applications, a very fast ISIS convergence is going to meet your real needs. You might have other needs, and we always want to optimize the technology. We will continue to do it, but it's already a good behavior. So I hope it's a fair technical answer to your question. So the conclusion is that IGP convergence needs to be optimized for Tight-SLA services. So I never use the word TOS. I don't like that word. But so I use the word Tight-SLA when I talk with customers. And that's often forgotten, that IGP convergence is a performance metric that you need to care about if you want to tighten your SLAs. We've done lots of developments to speed up convergence, especially without stability compromise, so that's the gain, obviously. The test results indicate that sub-second convergence is realistic, so I'm not signing the contract that in all the weird scenario you can think of, you will always make less than a second, but fairly and frankly, in the test scenario, we've been trying to be realistic and sometimes very demanding, and we see that once again the sub-second convergence is realistic. The second target that we are sometimes asked by some customers, it's the sub 100 milliseconds. With the data I have at this time, it's not possible with the current technology we have. That's not to say that we don't work on it, so we might one day get to it. If you want to get to that level of convergence with today's technology, you need to change the scheme totally, which is that ISIS has two fundamental properties that avoid this kind of convergence currently, but maybe it will evolve. You may find very nice ideas to make it better, but the two things are that it is distributed. It relies on your neighbors to help you to compute the routing table. So it means that you need to communicate things to your neighbors, and this will take time. And then it reacts to things. So if a link fails, you need to compute the routing table. And so if you want to really converge very fast, you change those two properties. And so you no longer ask your neighbors to help you, first thing, and you no longer compute after the failure. You pre-compute everything. And this is what MPLS fast reroute is doing. So in that explains why you can achieve this with MPLS fast reroute. Now, we will not go through that part of the tutorial. I would explain what the technology is, how to deploy it if you want to deploy it. What I would try to stress, again, it's a technical, my goal is to be technical, so we have it, Cisco has this kind of technology, but I want to say that you need to really make sure you have the benefit for it, because the deployment cost will be non-negligible. And so that's different from a marketing discussion. But it's a nice technology. Maybe you are in this context where you need it. So the other part of the talk is on the backbone diff-serve design. So here we're going to look at optimizing the loss, latency, and jitter. So first scheme on how to optimize loss, latency, and jitter, it's diff-serve with a single class. which is the over-provisioned backbone. So all of you run DiffServ with a single class. Some of you maybe have 2 classes. I know at least one that has 3 classes on the backbone today, which deployed what I'm going to explain. So the key idea behind DiffServ and behind DiffServ with a single class, which is the over-provisioning model, is that more bandwidth will give you better latency, better jitter, and better drop rate. That's, again, the purpose of this talk is to be pragmatic, to be focused on deployment, not on theory or academic study of schedulers and so on. So we'll try to be as simple as possible, as real it is with respect to actual deployments. It's not as complex as what people think it is in the backbone. At the edge, it's quite complex, but not in the backbone. So the other provisioning rule, this key principle, is that normally what people do is that when they reach an average load on a link of 50%, they upgrade the link. So I call it the over-provisioning factor, OP. So the idea with the over-provisioning backbone is that the OP factor is at least 2. You upgrade if you reach 50%, more or less. I take this slide coming from Stephen Kastner from Packet Design at main of 22, which is excellent presentation, and really an excellent presentation. There should be much more presentation on this, because it is one of those paper presentations that we can reference to actually show to people that you can achieve excellent quality of SLAs with IP technology. And otherwise you know it, you see it on your network, but nobody can reference it, and so everybody thinks that you need ATM to do it. So this slide report a testing that has been done on a tier 1 ISP in US, like maybe 1 year ago, where during 1 week, a 1 megabits per second probe was sent from Washington DC to SFO, and this graph plots the jitter for all those probes for 1 week. And Stephen showed that for this 1 week testing, the worst case jitter was 700 microseconds. So the other provisioning model works great. The simple idea that you need to put more bandwidth than what you need is basically a good principle. It works. And you can use data like this to make sure that indeed it works. And by the way, if you have this experience in your life to have run an ATM network, guess what? They use that rule a lot. So, because quite a lot of networks that are told to be CBR enabled are actually UBR and only managed like this on another provisioning manner. So it's always the same ideas. However, although I say it works well, I think this scheme has drawbacks. Why? Because it's very risky. It's risky because if you miss your capacity planning and suddenly you have congestion, you do not isolate traffic. And so if you have congestion suddenly, you will not treat your voice over IP packet better than your internet packet. You will maybe drop it, or you will schedule it after the internet packet. And to me, it's very suboptimal, which is internally the word I use for silly when I want to be polite. But to me, it's suboptimal because you could do better. The technology nowadays enables you to do better. Why not doing better? The second drawback that I see with this model is that it can be expensive. However, DiffServ allows you to have a cheaper model, but it will imply a more complex capacity management. So you will see that the DiffServ design that I'm going to explain comes in 2 steps. An easy one and then a more complex one. The easy one is focusing on removing the fake sharing, so bringing isolation between traffic. The second step in the design, which is more complex, is to try to have an economical benefit by putting more traffic on the network. But then you need to change the capacity management system. So why is it risky? It is risky because the target OP factor that you have is 2, and 2 is not a lot. Because a link failure, a node failure, and you can imagine that the rerouting of traffic can absorb an OP factor of 2. You can have unexpected traffic demands. You maybe have not analyzed all the failure scenarios. You may find out that your capacity planning scheme tells you that you need to upgrade a link, but you cannot do it for whatever reason. And then a good example that is, I think, to show this risk is that you can have a DOS attack in one of your services that you support on the same infrastructure, and this DOS attack on one service is going to affect the other service. And so the issue with the over-provisioning model, simple one with DiffServ with a single class, is the fate sharing. If something bad happens, it will affect whatever packets, and you don't try to make a difference between the packets. And again, I take another slide from Stephen Kastner, and I changed a bit the context in which I use that slide, so take his video to have his correct explanation of the slide, but I use it in another way. So the result was still quite good, but what I try to explain with this slide is that if something happens and you suddenly have packets that have a worse behavior, with DiffServ with a single class, you don't know what kind of packet you have here. It could be that these are the VPN or the voice over IP packet, and you have all your internet packets here, which is not what you would like to do. You would like to make sure that if something bad happens, the one you see here are your internet packets. And if it's very, very bad, you want the VPN packets to be there. A question?
I think those packets are actually hard. Those packets are actually hard to fly. The archive was very related, so I don't think there is going to have that.
So I agree with you. I said I use it in another context. I should have taken another slide. To be frank, I should have taken another slide. I say if something bad happens, if you have suddenly a link failure or a node failure, and you have more traffic than what you have, what you were capacity planning for, then you might see some variation in jitter, latency, drop rate. And so I'm just trying to have a visualization for it. And what I try to say is that the packet that will have this effect, you don't know which one it will be. You have fate sharing. They all share the same fate. And so I think that DiffServ helps you with this because it is going to help you to make sure that you treat the packet differently if one bad thing occurs in your network. So it's the service isolation. If you combine DiffServ with a change of your capacity planning system, you can also have an economical benefit. So I'll explain each after the other, and then finally I will conclude with the validation results to explain that what I explained for the backbone is mature technology. It's not complex, and it's available in the routers that you have on the market right now, and that you have for quite a long time. So I might be late by 5 minutes. So service isolation. DiffServ is much more, the IETF, RFCs, and so on, I think are more complex than what the technology is. So simply, it's a field in the packet header that allows you to recognize what kind of data you have in the payload. And so you're going to mark those packets with the DSCP to say it's a voice over IP packet, it's a VPN packet, or it's an internet packet, and that's it. The number of classes of service that we were looking at in the SLA introduction was 3 classes of service. A real-time, a business or premium data, and then an internet grade of service. So we're going to allocate a DSCP per aggregate class. So the ATF, the DiffServ RFCs recommend you some DSCPs for some the actual term is per hop behavior, but you can say queuing scheme, and it's the same. So they recommend you some DSCP values. In design, if you are in a real design, my recommendation is to not use the recommended value, because it's much better to, I think, based on my experience with this, to only use the free first bit on the left. The reason is that Ethernet has only a 3-bit field for QSID. MPLS has only a 3-bit field for QSID. So if you don't like MPLS, you might like Ethernet, so you still have the same problem. You see that at a certain time, you might want to transfer the QSIDs from Ethernet or MPLS to IP, or from IP to MPLS or Ethernet. And if you use 6 bits, while you actually only need 2 or 3, that's unoptimal, because you'll make your life much more complex when you have the problem. So if you do a design, try to only use 3 bits. And actually, I've never seen a design for the backbone that try to use more than 2 or 3 classes of service. So 3 bits, the 3 ones on the left, that's all what you need to use. But it's only a suggestion. So the low-level design that we worked on, we validated, and that has been deployed is this one. We have, for the real-time traffic, it goes in what is called the expedited forwarding per hop behavior. In practical term, it's simply a strict PQ, so which was available in iOS in 9.1 release, so it's an evolution of a PQ behavior. The capacity planning suggestion I would give is that to target an OP factor of 4, which means that the amount of voice over IP real-time per link should not be higher than 25%. If you reach that value, there is no logic for it. It could be 20 or 30, but if you reach that kind of value, you should upgrade the link. For the business or the premium data, you allocate it into an AF per hop behavior where you give 90% of the remaining bandwidth. So it means that you give almost all the bandwidth that remains after the PQ has been served. And then the internet class of service, you give it 10% of the remaining bandwidth, which means that you highly underbook it. It has a very small share of the bandwidth that is guaranteed. However, you know that the voice over IP will never use all the bandwidth, and the business will never use all the bandwidth either. So they will use the idle bandwidth, and that's the scheme. Because if you have a failure, if your capacity management fails, you will see that you will have congestion, but this is the class that will suffer. And so that's the only thing that you want to do with DivServ. It's to push back the back time on the class which you care the less. And you care the less for that class because the SLAs are looser for that class than the other one. This slide is to try to visualize the economical gain you can have with DivServ. So I compare 2 kinds of deployments. One which is the over-provisioning model with a single DivServ class, and you do your capacity planning on the aggregate where you want an OP factor of 2. And I compare it to a free class of service design with these capacity planning targets that I gave before. And this graph is plotting how much more internet traffic you can support on the backbone, knowing that you have a certain ratio of voice plus business. So if you have, for example, let's take this point, 10% of voice and 25% of business on your backbone, it means 35%. On an aggregate basis, you can only expect add 15% more of internet. If you are in a free class scheme and you do the capacity management on a per class of service basis, you see that you can add 45% of internet on this link. So 3 times more bandwidth in the DivServ case with 3 classes than in the DivServ case with 1 class. So that's the economical benefit. However, that step is not the first step I would suggest. It's maybe something that you can plan for a future time. Why? Because here there is a bit more complexity, because you need to change your capacity planning from an aggregate scheme to a per class scheme, and this is going to introduce complexity. However, the first gain, which is the isolation of traffic, this is not complex. This is not complex because that's typically the configuration that has been deployed. So you have a template that explains what I explain it. So it's 10 lines to say PQ 90%, 10%, and then on a per interface basis, you apply the template on the interface. This configuration is static. You never change it, so you don't need any clever tool to do it. You can do it manually or with script. So it's often not known. People think that they always need to tweak it, but not in this suggested design. You do it once, you don't change it. The capacity planning, there are two steps. The first step to have minimum complexity is to keep the current capacity planning, which is done on an aggregated basis. So the only benefit you get is the isolation between traffic, and then later on you can change your capacity planning to do it on a per class of service basis, and in that case, indeed you increase your capacity planning complexity, but the benefit you get out of it is that you can carry more traffic on your backbone. And so, depending on your case, it is justified or not to go to this second step. So, this is really the end of the presentation. The remaining 4 slides are used to give you the results, some of the results of the validation study that we did for this low-level design, to show that this technology is mature, it's not new, it's available for like 2 years, and it's not rocket science to use it. It's rocket science maybe to do it, to implement it, but not to use it. So the first thing that we want to validate is the quality of what is called the expedited forwarding behavior, or the PQ, the strict PQ behavior. So this is done in the lab with an engine 2, so an OC48 port. So it's a card that has been shipped in 2000, so it's 2 years old in terms of commercial use. In terms of technical implementation, it's 4 years old, so it's quite old. And you see that in this case, I inject 3 traffic coming from 3 OC48 coming from agent router tester, and I'm going to look at this curve. So this curve tells me that on the link on the test, the OC48, I had 51% of voice, 45% of business, and 150% of internet. So it means that I try to push 2.5 times more bandwidth than what I can on the link. So I have massive congestion. It's totally unrealistic. It's a very worst case behavior. On top of the 51% of voice at 200 packet size, I add for 3 minutes a real voice over IP phone call. And 3 minutes at the inter-packet gap for the coding scheme I use is 15,000 packets. We capture all of them, and we plot here the percentile distribution of the latency for the voice over IP packets. And so you see that, for example, 40% of the packet had a latency on the test bed, which is 2 router outs plus the router tester, of 110 microseconds. The percentile 100, which is the maximum latency computed for this test, is 130 microseconds. What we care is the jitter. The jitter is the variation of the delay. So it's very complex, and to compute it, to monitor it in the lab, and the router tester doesn't have this capability right now. So what we do is a worst case computation. The worst case jitter you will have is equal to the maximum latency you ever measured minus the minimum latency you have ever measured. And maybe you will never see actually this jitter, but it's the worst case you could see. So you see that here, the minimum one is 20 microseconds. It's the minimum time it takes to go through a GSR. So it's always 20 microseconds. It's the fixed value to go through the hardware of a 12,000. And then you see that the maximum latency measured is 130 microseconds. So it means that the worst case jitter per hop provided by the expedited forwarding implementation on this line card is 110 microseconds in a test case that is extremely worst case and extremely pessimistic. It is, if you remember, my budget per hop was 500, so it's 5 times better than my budget. Technically, it's hardware that has been built in '98, so it's old technology. If I do it with more recent hardware, so an engine 4, so a quad OC48, you see here an even more difficult test scenario where I have 75% of voice going in my PQ, 45% of business, and 150% of best effort. And this is tracking the average latency for voice, the minimum and the maximum. You see that the minimum is still 20, it's always 20. The maximum for an engine 4, Quad OC48, is 92 microseconds in our validation. It means that the worst case jitter you can have with the PQ behavior is 70 microseconds. You need to show those results to the people that tell you that ATM is needed to do good SLA services for IP. So there is nothing really rocket science even in the implementation. It's a DRR scheme that has been described by Varghese in 85. So it's simply that the implementation in a correct way on the hardware of this scheme that we have modified to add a strict PQ. So the engineer that is behind this implementation is very bright, because what he did is to take the experience we had with the 7200, the 7500, and the optimization of all the little things you could forget when you do the implementation of a scheduler. And here, the quality is very good, and you see it here. But once again, it's not rocket science, and that should be available on any router vendor. So here, it's 7 times better than the target 500 microseconds. The second validation rule that I want to check when I do this low-level design is that my AF per behavior, so this queuing behavior that allows to allocate bandwidth between queues, is correct. If I say 1090, it's 1580, it's 1090 and not 2070. So here again, it's pessimistic. I sent burst traffic into the PQ at an average rate of 30% and lots of burst. And on top of this, I have business queue and best effort queue, and I vary the rate between the two. So I do 1090, 1585, 2070, and so on. And what I put here is the inaccuracy of the bandwidth allocation. So the difference between what you expect and what you measure in a test case where you have burst traffic into the PQ. So it's very difficult for the router to do it, because he always switches back from the AFQs to go to the PQs and service the voice over IP packets. And then he goes back to the data queues, and he has to have counters, DRR counters, to remember where he was in his schedule. So it's a very difficult test, and you see that the bandwidth accuracy is below 0.1%. So the bandwidth inaccuracy is below 0.1%. What I do not show, because to me it's obvious, but it's often asked, with this kind of mature technology, you enable it, obviously you don't lose any performance because it's in hardware. So if someone tells me that an engine 0 will fail this test, or will have an accuracy of 1% and its CPU will be burning if you do this kind of testing, I will say yes, but an engine 0 is 5 years old. It has been designed in 97, so I agree with this. An engine 0 is old technology compared to this, but if you look at what to me is not non-legacy, so engine 2, engine 3, engine 4, new line cars that have been built shipped since 2000, that's something that you have in hardware, and that's the quality you can have.
Last slides you showed were made with the peak conferences for the weighted rate from page 2. You showed the slide.
Weighted rate has nothing to. You need to configure a dropper, so you need to configure weighted rate, but it will not affect the quality of those tests. You will see its effect here. So. Here, and then I'm done for the presentation. I don't want to argue more, but I'll conclude after this slide. It's a very important property that I validate here. I said that when you do the surf, or even you do the over-provisioning model, the principle you use is that if you have more bandwidth than what you use, you'll get low latency, low jitter. And you saw that the suggested design gives 90% of the bandwidth to the business queue. So the idea is to give more bandwidth than what this queue is going to use. Why? To give it low latency so that you can add a latency commitment to this class of service. So I want to validate it. And so what I do here is that on my link on the test, my line card on the test, I send voice over IP packet in the PQ, again in bursty behavior, to be in the worst case. And then I congest my internet queue with 2 times more bandwidth than the link can carry. So I have massive congestion and I have bursty traffic. And then what I do is I vary the load in the business queue. And I track the maximum latency of the business packets in the business queue. And so what you see here is very good because it tells you that because it's done in hardware, it is deterministic. You see that if your capacity planning is correct, the maximum latency you will see, as long as the business queue is not overloaded, is smaller than 160 microseconds. So you could even use a well-capacity planned business queue to still support voice over IP. You would still be like 3-4 times better than the budget for voice over IP. And so that's a very important rule that you can have. If you have a business queue that is well-capacity planned, the latency will be very good. The other internet queue is not going to affect the latency. And this is a major improvement if you compare to like a 7200 or 7500, where it's much more complex because it's handled by CPU. So that's how you can see that the evolution of the technology. And then what we do also, we then congest the queue. So once we reach the 100 loading, it means the queue becomes loaded. You never want to operate your network in this context for the business class. And then what you expect there is that the queue is going to grow, and grow up to a point where it is controlled by red. And the tuning we use in our the suggested design is with a pipe size of 100 milliseconds. And so we expect that if we keep unloading that queue and overloading it, it will go to a maximum latency of 100 milliseconds, which is what we saw here. And again, I was not expecting that it would indeed do this. I was expecting that it would have some deviation, so it's a good behavior as well. But it's not an important one, because you will operate your network at 50, you will operate that queue at less than 50 persons. So what you see is that you have very low risk to have high latency if you operate it correctly. So I'm going to skip this and conclude. If you care for tightening the SLAs on an IP backbone, you should focus on controlling and tightening loss, latency, and jitter. Another performance metric that you should think of is convergence. It's often forgotten when you talk about SLAs, but it has a strong impact on availability, loss rate, and service perception. What I try to do, which is not easy, is to advocate the case for this search. The way I try to do it is not to try to do a marketing talk to say my router is doing it very well. I think that any other router vendor can do the same. It's nothing like at the end it's not rocket science. It simply needs to be well done in the hardware. So what I try to say with those results is that the technology is mature, it's available, it doesn't cost you more when you pay Cisco for it, it's on the line card. And it doesn't consume, it doesn't lose performance when you do it because it's in hardware. I try to say that you can segment a bit served deployment in 2 steps. You can have an easy gain, which is the isolation between traffic, and then you might update your capacity planning to have also an economical benefit in terms of utilization of your backbone, but this I recognize that it's more complex. It's a change of your capacity planning scheme. If we would be in the full day tutorial, I would go through TE and DisServe TE. These are nice technologies, but my point would be to try to say that they are good technologies with good benefits, but with non-negligible deployment cost. So when you look at this, you might want to really check on a case-by-case basis whether you really benefit from this, whether the benefits are higher than the cost. But I'm not saying this to say that we don't support it. It's, again, I'm trying to give a technical analysis at this problem. On the convergence side, I spend my time on ISIS subsegments to try to explain that it's not rocket science, that the technology has evolved, and that you can optimize the convergence of ISIS to a subsegment level. And to me, if you care for SLAs, that's a step that you should look at for optimizing your backbone. If you want to go to the sub 100 milliseconds target, you need to consider technologies such as MPLS faster route. It works, it's available. We did lots of work on it, so marketingly we will talk a lot about it. Technically, you should take a router that allows you to do it, but in terms of deployment phase, you might want to consider at what time you want to do it, because again, the deployment cost, the operation costs are non-negligible, and so you need to analyze whether you have the benefits to justify it. So that's the end of my presentation. If you have any question, feel free to ask them. Stefano is in the back, so we did together the ISIS work to optimize the conversion. So he did all the coding, so he did really the work. So if you have any question, you can also ask him. And otherwise, thank you for